Actually, many researchers and actually faculty, they may know about how to tune Ziegler-Nichols and Cohen-Cohn, other conventional tuning methods. So this is also conventional tuning methods. Actually, this is new, that is root locus technique. By using that root locus technique, so how to tune that PID values, KP and KI and KD. So that is a very important tuning of the parameters. That PID controller is very important. Actually, many researchers, they maybe use trial and error values on that KP, KA and KD. So that main objective of this session, after this session, so obviously that faculty will be able to design the PID controller parameters by using this root locus technique. If time permits, I'm also ready to explain the design of PID controllers using PID controllers in frequency domain. So that is also, if time permits, I'm ready to explain. Okay. So that is the title of this topic. This will be helpful for your future research, and that you maybe share this knowledge to your student, final year students, and then pre-final year students. So they are doing a lot of projects now. So that this knowledge may be helpful for your student also. So after attending this FDP, okay. Now that overall presentation. Yeah, that is outline of this presentation. So I'm going to explain the introduction part. So in that introduction, so what is control system? So what is the importance of the controller? Actually, this session, we are going to talk about only PID controllers. So we know that PID is a conventional controller. Actually, recent days, many research they used this conventional controllers for comparing purpose, existing controllers. Suppose the research maybe do some tuning algorithm for other than that conventional. So they may be compared with this PID controllers. So still many researchers they are using the PID controllers. These are most versatile, so then efficient. So that's why that many researchers preferred this PID controller. So that introduction part. So what is control system? Then why we go for controller? Then after introduce that controller, what will happen in that output? So everything we are going to discuss. Actually, that this session also we are going to use MATLAB coding also. So I'm ready. I'm also explaining that MATLAB coding with all tuning method we have to verify. Okay. So that outline of this presentation, the different types of PID, what are the PID types are available. Then the main objective of this session, how to design the PI controller parameters, PD controller parameters, and PID controller parameters using that root locus technique. If time permits, I'm also ready to explain that frequency domain also. Okay. So as we know that, so in electrical and electronics engineering, so actually we are dealing many systems. So that various domains are there. So control system is one of the major domain. In many faculties and then research, they are doing research in power electronics, power systems, and then other areas. So definitely they may deal systems. So whenever we can handle that system, any system, so that control system, closed loop control system is plays a major role. Okay, suppose you are going to for example, in power electronics. So you may design, you may handle any power electronic circuits like buck boost converter and any converters. So definitely that controlling part is important. Suppose on the closed loop system that it consists of PID controller, that tuning of that parameters. Here, this whole session, then how to tuning, because that poor tuning definitely will lead a poor performance. Actually, that many of the researchers, they may be they used trial and error values. For example, they may be put KPK, KD values like 1, 2, 3 like that. So they may use the trial values. So that main objective of this session, so that all faculty will be able to design the KPK, KD values with desired performance of the system. Okay, so that automatic control system, definitely that optimal controller design in both offline and online, any industrial applications, any other applications. So definitely that improving that physical and operating constraints like stability, so quick response, so robustness. These are the important parameters. So whenever we can introduce that controller, so that optimal controller, that is very important, no? Design of that optimal controller. So that's why we go for the tuning, efficient tuning parameters. So we know that, so all of them know about the PID controller. So has been widely used for many years due to its simplicity, then flexibility and efficiency. Okay. Then many of the researchers and industry application, they preferred only PI controllers. So that the importance of that PI controller and the tuning of KP and tau I is very important, or KI. Okay, the controller tuning is very much essential for that satisfactory of the closed loop system. So whenever we have a desired performance, for example, the time domain specifications. So whenever we can use this root locus technique, so we have a time domain spec like delay time, rise time, then peak overshoot, so then settling time, then a steady state error. Suppose I'm going to design, I'm going to develop on good control system. So that controller is very important. Then the tuning based on that our desired spec. Suppose I'm going to refer time domain spec. So I go for root locus technique. Suppose my specifications are a phase margin or gain margin or gain crossover frequency. Then phase crossover frequency means we go for frequency domain. So we know that then frequency domain, we can use Bode plot, the technique using that Bode plot. So we can find out that phase margin, gain margin, gain crossover frequency, and phase crossover frequency, everything. Suppose I'm working in the time domain. So that parameters we know. So rise time, peak time, overshoot. Then overshoot, obviously that is related with the damping ratio, then natural frequency. So in this RLT technique, the root locus technique, so we are going to consider these two parameters are very important. That these two parameters, theta and omega n. So this PID controller tuning using this root locus technique, in this case, we are going to consider the two parameters, so like damping ratio and natural frequency. Okay. So whenever the tuning, whenever we can tune the pakka, the controller tuning is the efficient means, obviously we will get a very good closed loop performance. So in terms of stability and reducing the rise time, peak overshoot, settling time, then steady state error. Okay. So keep it in our mind whenever we talk about, whenever we can use that root locus technique. So we are going to deal these parameters, rise time, peak time, settling time, then damping ratio, a natural frequency. Okay. So using this parameter, we are going to design that KP, KA and KD values. Yeah. So we know that this is cascade. I'm using this cascade connection with open loop transfer function. So we know that the G of S is nothing but that is open loop transfer function. So in this session, we are going to consider transfer function. So Laplace transform of output divided by Laplace transform of input with zero initial condition. So that mathematical model we are going to use. Then that I can introduce in series of that G of S, and that is GC of S. So now that is in this session. So we are going to discuss about only the GC of S, how to tune KP, KI and KD. Okay. So after tuning these controller values, so we have to check that output. We have to verify that design. we have to verify the design that G out of S equal to GC of S into G of S. So G of S, we know that is nothing but open loop transfer function. Here GC of S is nothing but controller transfer function. Okay, so that we are going to derive or design this controller transfer function. So after that, we have to check that G naught of S. G naught of S is nothing but closed loop. Actually, open loop transfer function with controller. That is the meaning is compensated system. So we call compensated system. So without controller, this system we call uncompensated system. No, uncompensated system. So we are going to design that GC of S. So we know that that controller, that GC of S, that controller output E of S, that is nothing but controlled variable or actuating signal. So that is that U of t is proportional to E of t. So that controlled signal or actuating signal I can represent it in U of t, that is in terms of time domain. So is proportional to E of t. Okay. So based on that concept, we are going to derive that Kp, Ki, and Kp, Ki, and Kd. So the controller with transfer function GC of S can be introduced in cascade with open loop transfer function G of S. Okay. So we know that that is different types of controllers available. So proportional controller, then proportional plus integral controller, proportional plus derivative controller, then proportional plus integral plus derivative controller. So in this session, we are going to design these three controller using RLT. So in this RLT design, so I'm going to consider theta and omega n. So theta is nothing but damping ratio. So omega n is nothing but our natural frequency. So when the unit is radian per second. Okay. So these two parameters, using these two parameters, we are going to design Kp, Ki, and Kd. Okay. So mostly we can't use this proportional controller. So why? Because of that, whenever we can use this proportional controller alone, so that it will produce constant steady state error. Okay. So that's why we can't use that P controller. So most of the cases that based on that system performance, we are going to choose PI, PD, and PID. It depends on your requirement. Yeah, we know that that is a proportional controller is a device that produce output signal U of t is nothing but controlled signal or actuating signal with proportional to the input E of t. So the transfer function of that PI controller is Kp. Okay. So this is nothing but proportional gain or proportional constant or gain. Okay. So that meaning is that Kp then series with G of S. Okay. So here our set point is there. Okay. So that G naught of S equal to Kp into G of S. Okay. So mostly this proportional controller we can't use because of that problem. That is it will produce constant steady state error. Okay. So next, proportional integral controller. So the device produce an output signal U of t. That is U of t is proportional to the input signal EFT and proportional to the integral of input signal EFT, that is integral of EFT. Okay, so after we will get the EFT equal to Kp EFT plus Ki integral of EFT. So after taking Laplace transform, we will get the transfer function V of s divided by E of s divided by E of s, that is Kp plus Ki by s. So there is a typical transfer function of this PI controller. So whenever we can use this PI controller, that steady state error is improves. Actually, we know that response, no. Just I'm recalling. So we know that time response or step response. There are two parts. One is a transient response. Another one is steady state error. So first part we can call the transient response. Then second part is a steady state response. So, okay. So whenever we can introduce the PI controller, the steady state error or final value is improves. So only this is advantage, but disadvantage is whenever we can introduce this PI controller, so that order of the system is increased by 1. System increased by 1. So because of that, we know now Kp plus 1, that is denominator s is there now. So whenever we can multiply with g of s, obviously that order of the system will be increased. That is one big disadvantage. So whenever we can introduce that PI controller. So next controller is a proportional plus a derivative controller. So that output signal is proportional to input signal EFT plus proportional to the derivative of input signal. So that is d by dt of EFT. So EFT is equal to Kp into EFT plus Kd Kd d by dt EFT. So after taking Laplace transform, we will get Kp plus Kds. Okay, Kp is nothing but proportional gain or constant. Then Kd is derivative gain or constant. Okay. So this is transfer function of PD controller. So whenever we can introduce this controller, so that peak overshoot is reduces. So whenever we can use this PD controller, that peak overshoot will be reduced. Okay. Then yeah, that is PID controller. So that E of t is proportional to E of t plus integral of E of t plus d by dt of E of t. So after taking Laplace transform, we will get Kp plus Ki by s plus Kds. So Kp is nothing but proportional gain, Ki is nothing but integral gain, so Kd is nothing but derivative gain. So whenever we can introduce this PID controller, so that both transient and steady state response also improves. Okay. So now we know that all introduction part, what transfer function of transfer function of PI controller, PD controller, and PID controller. Okay, so now we are going to go for the design of KPK KD values by using root locus technique. Okay, so up to now we discussed that introduction part. Okay, that closed loop system, then how to design that KP, sorry, that transfer function of that different types of PID controllers. So now we go for entering that topic. So design a PID controller parameters using tuning by using root locus technique. So already I told in this technique, the PID controller can be introduced in cascade with open loop system, so that it can have a pair of dominant poles. Yeah. So that we know that no dominant pole I can denote in terms of SD, that is equal to minus theta omega n plus or minus j omega n. So plus or minus j omega n root of 1 minus theta square. So listen, so in this technique, the PID controller can be introduced with cascade with open loop system. So we can introduce that dominant pole, pair of dominant closed loop poles to satisfy a specified time domain spec like damping ratio and natural frequency. So here our desired parameters are desired spec or theta and omega n. And also I can have a pair of dominant closed loop poles. This dominant is SD dominant pole to satisfy the specified time specifications whenever we can use this theta and omega n. So now I'm going to use this equation. So is D equal to minus theta. Theta is nothing but damping ratio. So omega n is nothing but natural frequency. So that value we can introduce in terms of radian per second. So this formula I'm going to use. Yeah, the procedure for design of PI, PD and PID controller. Okay, to calculate magnitude and phase. Listen, actually, so what I'm telling here, we are going to use theta and omega n. Okay, for example, theta equal to 0.5, then omega n equal to 4 radian per second. Okay, so I can substitute these two values, so I will get one dominant pole. So that dominant pole, from the dominant pole, so I'm going to calculate D and beta. So D is nothing but magnitude of the dominant pole. So magnitude of dominant pole, then beta is nothing but phase of that dominant pole. Okay, so this is magnitude, this is phase of the dominant pole. Okay, that is first step. So using these two values, theta and omega n, so we will check in MATLAB also. We can use and verify that answer also. Okay, so step one, using theta and omega n, so we are going to calculate D and beta. Okay, so next step, so to determine the magnitude and phase of G of S. For example, I have a system G of S. For example, 10 divided by S plus 1 into S plus 5. Okay, so now I'm replace that S equal to SD. Replace S equal to SD. So after replacing S equal to SD, so I will calculate that magnitude of G of SD and phase of G of SD. So this is, I can denote AD. Here I can denote PID. So now I have four values: D, beta, and AD, and PID. So using these 4 values, so I'm going to frame that KP, KI, and KD. So we know the transfer function. So using these 4 values, so I'm going to calculate KP, KI, and KD. So formula is there. That formula, yeah. Actually, how to arrive this formula? We have very big derivation. I think this session no need for this derivation. You just know about the formula. So using this formula, we are going to calculate KI, KP for PI controller. So step 3. Suppose we are going to introduce a PI controller. We know that controller transfer function of that PI is nothing but KP plus KI by S. So using these 2 formula, so I am going to calculate KI and KP. So we know that D, PID, AD, beta. Okay. Then KI, from this formula, we know that KI value. After that, we have to substitute this KI here. We will get KP. So with a spec theta and omega n. So using the specifications, now we find out that KP and KI values. Okay, so after find out this KI and KP value, we are placing in that GCFS. So now we got the GCFS transfer function for the desired spec. So we know that GFS, then GCFS. We can multiply both because these 2 blocks are in series. No, we can multiply that. So after that, we have to check that answer, whether the answers are correct or not. We will check one by one. So now this is the procedure to design KP, KI, and KD. Yeah. Suppose I'm going to introduce PD. This formula I'm going to use. Then KP. So whenever I can introduce PD controller, KI equal to 0. So we know that transfer function of the PD, KP plus KDS. So after calculating these values, so we can place this value. We can place the KP and KD values. So then we will get GFS, the transfer function. Then PID controller, yeah. That formula is there. So before calculating that KD, we must know about KI. Then how to calculate KI? So we have a procedure. So that I determine the integral constant from specified error constant. That is ESS. That is ESS. Steady state error constant. That is, so that compensated system meet that error constant. For example, my system is type 0. For type 0 means then how to identify the type of the system? So we then from the transfer function, the denominator, that poles, how many poles are lying at that origin? So from the lying of that poles, so we will find out type 0, type 1, type 2. So type 0 means here there is no poles lying at origin. Here there is no poles lying at origin, we call type 0. Suppose only 1 pole is lying at origin, we call type 1. 2 poles, type 2, like that. So for example, I have a type 0 system. So meaning is here you just take the same system. Yeah, you can take this system. So 10 divided by s plus 1 divided by s plus 5. Here 2 roots are there, -1 and -5 in denominator. There is no poles are lying at origin. So we call this is type 0 system. Okay. For example, I have type 0 system. Here I'm going to consider that velocity error constant. We know that formula. So KV equal to limit s tends to 0, s into GC of s and G of s. We know GC of s, we know G of s. So we can replace, we can put s equal to 0, then we will get KV. Okay, here KV equal to KI. I'm going to consider KV equal to KI. So based on that error constant. So KI is determined by using that error constant, and then we will find out KD, KP as such. So D is there, AD is there, then PID, then KI values, we are going to find out KP, KI, then KD. Okay, so this is the procedure. Up to now, what we discussed, procedure for designing the KP, KA, KD values by using root locus technique. So that when we can introduce that theta and omega n. Okay. Yeah. So now we go for MATLAB coding. Okay. Now in time domain, yeah, now I can take PD controller. You just look at the, my screen is visible, sir. Can anyone please respond? Is it
No,
visible
sir.
that MATLAB coding?
No, sir. PPT is only available.
Oh, PPT is once again. Actually, I'm sharing only that PPT. Yeah. So now, sir, now can anyone please?
Yes, sir.
Yeah. Actually, what I told, using that root locus technique. So we are going to use only that theta and omega n. You just look at the program. Here I am taking theta equal to 0.8. Then omega n equal to 2 radian per second. So I'm using the dominant pole, that formula. So SD equal to minus theta omega n plus j omega n plus j omega n root of 1 minus theta square. That formula I'm using. So using the theta and omega n, so I'll get SD dominant pole. So now from that dominant pole, I'll find out D and beta. So absolute value, that is the magnitude of that SD, then beta equal to phase angle of that SD. Whenever I can, whenever that S is replaced by SD. So now the D and beta, then I'm going to introduce my system. Here I'm taking that system. For here I'm going to design PD. Okay, the system I am going to introduce 20 divided by S into S plus 2 into S plus 4. So now I'm replacing that S equal to SD. So after substituting S equal to SD, I will get AD and PID. Okay, so then using this formula KP and KD formula, I will get KP and KD values by using the D, beta, AD and PID. So next I will get the transfer function of the PD controller, GC. So next I can find out that the G naught compensated system. So then next I will find out the closed loop of that system, then verification part. So before execute this program, so now I'm going to verify my system is stable or not, and the meaning is it achieved final value or not. So I have a MATLAB coding. Let me check. So what I told, yeah, this program. So now I'm checking without feedback. So without feedback, I'm checking that step response of the system. So now I'm executing what? Yeah. Let me check that response. So step I'm giving, step input is given. Yeah, G. Yeah, I think that the response is visible. You just check it, sir. That's final value does not reach. Am I correct, sir? We are getting some that is the system is unstable, I think. So we are getting that step response that output does not reach our required input one. So that's why we go for a controller. So anyway, I will check once again the closed loop also, closed loop response. C equal to feedback of that G comma 1. So now I'm checking that closed loop response of the system. So in open loop response, so does not reach output. In closed loop also, you just check it the response. Actually, that final value is reached 1. That final value is reached 1. But that overshoot, the peak overshoot is maximum. So now I'm using PD controller. What I told, so when I'm introducing that PD controller, that overshoot will be reduced. So now let me check. Actually, the system that without controller, that closed loop response, it reaches final output. But that you check that overshoot, no, is high. Let me check that overshoot. 48.3% is there. So now I'm going to reduce that overshoot by using that PD controller. Okay. Now I go for that. Program. So now I'm executing this program. You just verify. I think the screen is visible. Yeah, you can check it, sir. That response, that overshoot will be reduced. We will get quick response after introducing the PD controller with root locus technique. Let me check. Overshoot is 2.26, and also we arrived at that final output. Okay, you just check it, sir, that this is SD is nothing but dominant pole, then D, beta, AD, then PID, then KP value 0.56, then KD value 0.24. But most of the time, the research they are putting KP equal to 1, KD equal to 1, like that. But here we tuning the parameters in a very good way using that theta and omega n values. Okay, this is a compensated system. So this is a closed loop response of the system. So here I verified, listen, actually, this is final closed loop transfer function. So again, I'm substituting the SD value, the verification part. I just see the program. So again, here I got that the G naught of S no. So after G naught of S, so we will get the transfer function. Again, that transfer function I am placing S equal to the same dominant pole. I am verifying that answer magnitude and pi d. Use verify that answer. No, AD equal to 1. Then pi d equal to minus 180 degree. Sir, actually in MATLAB that phase that MATLAB represented in radians. Okay, so whenever we can convert this radiant into a degree, so we will get minus 180 degree, minus 180 degree. So that verification part, so what we are getting, some magnitude of 1, angle of minus 180 degree. So that in root locus technique, that root minus 1 is lying on the dominant pole. That meaning is, so whenever we can introduce that root locus, once again, then how to verify that design. So after getting that G naught of S, that is a compensated system. So again we can substitute the dominant pole. So we will get a magnitude of 1, angle of minus 180 degree. So that polar to rectangular we will get -1. So that the meaning is that -1. So G naught of SD, the root locus will pass through the dominant pole. So the design is verified. So the meaning is, so what we are getting, sir, this slide is visible. Sir, can anyone? My slide is visible, the PPT.
Yes, sir.
Yeah.
Visible.
Actually, what we are getting, that G naught of S equal to GC of S and G of S. So after that verification part, here I am substituting S equal to SD. So what we are getting? So that G naught of SD equal to 1, angle of minus 180 degree. So that -1. So the meaning is the G naught of SD -1, the root locus will pass through dominant pole. So hence the design is verified. The design is accepted. So here I am proving with MATLAB coding. So after introduce that controller, PID controller, that overshoot is reduced, and also we will get quick response. So next one, PI controller. Yeah, PI controller. Here, that theta value I'm taking 0.9, omega n 2.5. Here I have a system 4 divided by S plus 1 divided into S plus 5. So same procedure. So now I'm going to, that only thing, the transfer function is changing, no? Kp plus Ki by S. Okay. So now I'm executing this program. So before that, I'm going to verify that open loop response. This transfer function. Four divided by S plus 1 into S plus 5. So closed loop response I'm going to verify. You just see the output. The final value does not reach. The final value is not reached. Final value equal to 0.4. So whenever we can use a step command, we will get 1. No, that output reaches to 1. But so that closed loop response, we are getting 0.4. The meaning is, so we can't, that is a response and the output does not reach at 1. So now we are going to introduce that PI controller for that system. So after execution, what we are getting? Okay, once again. You see that? Yeah, now that output is reaches 1. So see the values. See that values D, beta. So this is actual system we are importing. Then this is dominant pole. After substituting S equal to SD, then AD, PID, then KI, then KP, then GC of S, then G naught of S. So after that, I am verifying that answer magnitude of 1 PID. So we will get -1. The design is verified. That is accepted one. Then PID controller. Yeah, now we are checking that closed loop response of the PID controller. Here I'm using 75 divided by s plus 1 into s plus 3 into s plus 8. So now I'm checking that the response, closed loop response. Yeah. You see the output, no, that output does not reach 1. That final value equal to here 0.75, but we want 1. So that is the output response not reach that final value. So now we are going to introduce that PID controller. So here I'm using theta equal to 0.8, then omega n equal to 2.5, then a dominant pole. Okay. Yeah, already I told that Ki value it can be find out by using that velocity error constant Kv. So here I can use that formula Kv equal to limit s tends to 0 s into g into gc of s. Already I told. From that formula here I can consider ESS equal to 0.08. So from the Kv equal to 1 by ESS. So after that I can substitute s equal to 0, that is limit s tends to 0. So I will get Ki value Kv divided by G1. That is the constant value of G1 of s. So then Ki value I'm going to find out using this error constant. Then Kp and Kd as such formula. So now I'm executing this program. Yeah, just the output response. It reaches to 1. Reaches 1. Okay, just see the values of D, beta. Then this is the actual system we are importing. Then AD, PID, then Ki, Kd, Kp. Then we will verify that answer. Magnitude of 1, angle of 180 degree. Actually, up to this, so I explained that procedure for tuning of the Kp, Ki, Kd value with the theta and omega n. That is root locus technique value. Okay. So and also we verified in MATLAB. So up to this, any doubts? If now time is only 11. So next half an hour better I will explain that frequency domain also. So up to this, any doubts? Anybody's?
No, sir, it's very clear.
Okay, sir. Actually, the design part, then formula, and then procedure, everything is available in textbook. So on the main motto of this session, so at least that sharing of that knowledge. So hereafter, that faculty or researchers, they may know about how to design KPKA, KD values. So in actually in many of the researchers, they used Ziegler-Nichols and Kogan code. So when we use that Ziegler-Nichols method, so we want open loop response. We want to calculate that L, the time constant, everything. So that is also very old, the Ziegler-Nichols, everything. This is also existing, but so at least we have to share this knowledge to student, so they may be used in that final year projects. So I think they may know about that also coding, MATLAB coding, how to write coding, everything. Actually, my coding, so when you just replace the G and theta and omega n, so these three values you have to import immediately. We will get all answer with verification. Okay, so now we go for that frequency domain. That yeah, design of PI, PD, PID controllers using frequency domain. So Up to now, we discussed the time domain values, that is parameters. Here in frequency domain, then how to design the Kp, Ki, Kd values with a desired specification of phase margin. Here I'm considering that phase margin. I can represent this symbol. That desired phase margin I can represent. Then gain margin, gain crossover frequency, omega n, omega 1. Here in frequency domain, the tuning of Kp, Ki, Kd values designed to satisfy the specified desired phase margin and that is given gain crossover frequency. Using these two values, using these two parameters, that is frequency domain parameters, we know that what are the frequency domain spec, gain margin, then phase margin, then bandwidth, then gain crossover frequency, omega GC, then phase crossover frequency, omega PC. So these are some the frequency domain spec we know, but in this case, so I'm going to consider this phase margin, desired phase margin, and desired gain crossover frequency omega n. So in root locus technique, what we used theta and omega n. No, here we can use desired phase margin and omega. We know that basic definition of that phase margin. So that is 180 degree plus pi. So adding of that additional phase, that we know that the basic definition. So phase margin equal to 180 degree plus pi. Okay. So this pi is nothing but phase of uncompensated system. So let me start. Yeah, step 1. So we know that PI controller transfer function, PD controller transfer function, PID controller transfer function. So that now we are going to find out the values Kp, Ki, Kd with the desired value of phase margin and gain crossover frequency. Step 1. So now I'm replacing. So we know that. So whenever we can deal, whenever we can use in frequency domain, that we can replace S equal to j omega. That is S equal to j omega. So now I'm considering this omega equal to omega 1. So here we know that omega 1 is nothing but the desired, that is given gain crossover frequency. So from after substituting this omega equal to omega 1, so we will get A1 and pi 1. So A1 is nothing but magnitude of G of j omega at omega equal to omega 1. Here pi 1 is nothing but phase of G of j omega at omega equal to omega 1. Okay, so now we are getting two values, A1 and pi 1. So next one, step 2, determine the phase margin of uncompensated system and angle to be contributed by controller to achieve the desired phase margin. So already I told that is we can represent the phase margin, that is U indicates uncompensated system. Then how to find out this uncompensated phase margin? Whenever we can substitute S equal to j omega, then omega equal to omega 1. So that open loop transfer function, that is uncompensated phase margin from that open loop response. So now I'm going to find out that RD, sorry, desired phase margin. Okay, so desired phase margin after substituting this omega equal to omega 1. Then how to find out RD? That is, RD is given. No, that RD is nothing but our desired phase margin. Okay, then theta. So I'm going to calculate theta, that phase angle of that controller, omega equal to omega 1. Then how to find out the theta? So we have a formula. Yeah. Then step 1. Then to find out uncompensated phase margin using this formula. So 180° plus pi 1. Okay. Then theta. Theta equal to V, that desired phase margin is given. We know that is our required phase margin minus this uncompensated phase margin. We will get theta. So now I'm getting three values. A1, pi 1, and theta. Then how to get this theta? That is angle contributed to the controller, theta, the desired phase margin minus uncompensated phase margin. So then we can use this formula. So this is also, we have big derivation. We can leave it now. So we can use this formula. So we know theta, we know omega 1, we know A1. So omega 1 is that is a given spec, that is a gain crossover frequency. Then RD also is spec you can use to design KP, KD, and KD. So KP formula, then KD formula is there. So for using these two formula, we will calculate KP, KD, then substitute in that GC of S, KP plus KDS for that PD controller. So next PI controller, yeah, omega 1 sin theta by A1, KP equal to cos theta by A1. So using, after find out this KP and KI, so we can frame that transfer function controller KP plus KI by S. Okay. In PID controller again, so using this error constant. For example, your type 1 system, so we can use KV, that is limit S tends to 0 into S into GC of S into G of S. So from this velocity error constant, so we will find out that KI. Yeah, KP, the same formula, then KD, KI equal to KV. So after find out that value, so we can frame that the controller equation KP plus KI by S plus KDS. This is PID controller transfer function. Yeah, this is then final verification. So G naught of S equal to GC of S into G of S. So now we can able to verify that concept. The PD controller, sorry. Yeah. So this program, I'm using this transfer function 10 divided by S into 1 plus 2 plus S. Actually, I rewrite that equation now. Then 2 plus S plus 2 and S plus 1. Okay. Let me check that open loop response. Using that Bode response, we can use that command Bode. So we will check actual phase margin of the that open loop system. Let me check. Here the transfer function is 10 divided by s plus 2 into s plus 1. So 1 minute. So I'm checking the transfer function is correct or not once again. Actually, the transfer function is that actual transfer function is 5 divided by s into s plus 0.5 into s plus 1. Actually, I simplify that equation now. Okay, once again, or else we can use that same transfer function, no problem. So now I'm copying that open loop transfer function and checking that open loop phase margin, everything. So yeah, let me check that phase margin. That phase margin is now indicates 51.7. Actually, now I'm checking that phase margin of that open loop transfer function, which I was imported in that program. Okay, so that phase margin now indicates 51.7, and that omega, at frequency in radian 5.18. So this is actual phase margin of the that open loop transfer function. So now I'm going to design the PI controller values KP and KI for our required value. Okay. Yeah. So what I'm telling, so this is PI, no, that is PID. So what I'm here, I have two spec omega equal to 1.2. Then here the desired phase margin, I'm writing in radian. Let me check the in terms of degree. Let me check 30 degree. So I'm going to design the PI controller. Here my desired phase margin equal to 30 degree. Then omega 1 equal to 1.2. So these two parameters are my design. That is my required or specified values. So after introducing that PD controller, that response, that is output, will give that the desired performance equal to 30 degree, then omega 1 equal to 1.2. So now what we are getting in open loop response, actually, so what we are getting now, let me check once again. Sorry. No, I think transfer function. Actually, we got some value, no, that is that uncompensated phase margin and omega 1. So we are getting some irrelevant values. Okay, when I was checking that open press point. But the required things 30 degree and 1.2 radian per second we want. Let me check. Yeah. So I told that the desired phase margin equal to 30 degree, that the desired omega 1 equal to 1.2. Okay. So now I'm going to verify this answer. After executing that, after find out that KP and KD values, let me check. You verify that answer. Actually, we are getting 30 degree, 30.1 now. So, oh, sorry. So 30.1 phase margin, then 1.2 frequency. We got it, no? So after design that PD controller, let me check one by one. Yeah, that is PID, Pi1, A1, KP, KD values. Then I'm verifying that answer. Magnitude I will get 1. Then pi value actually minus 2.614. That is nothing but you check that final answer, no, 0.52. So what we import means here 0.52. That value also we can import as a desired phase margin 0.52. So the design also verified by that coding. You check now 0.52. That is compensated phase margin. So we get it. No, that answer is we get it 30.1 and 1.2. So my design is verified. Then PID, let me check here. I'm giving omega equal to 4. Then the transfer function is 100 divided by s plus 1 into s plus 2 into s plus 10. Here that desired phase margin is 45 degree. The desired phase margin is 45 degree. So now I'm execute this program PID. 16. KI. KD, some problem in that omega 1. Yeah. So now once again something is wrong. Well, this is different program. PI, sorry, this PID, yeah, is there. that phase margin 45 degree, and that radian per second 4. We got it. 4 radian per second and 45 degree. So this is typical tuning of Kp, Ki, and Kd values for the transfer function 100 divided by s plus 1 into s plus 2 into s plus 10. So once again, I can run this program. Just look at the values. Yeah, this is transfer function of the PID controller design, that is G of S. Then H, after substituting that omega equal to omega 1, then A1, pi 1, Kp, Kd, Ki, then output transfer, closed loop transfer function. That here I verified that magnitude is 1. Here minus 2.35. That is angle is given, that is 0.78. So that is our design value. No, let me check. Yeah, 45 degree. Then response also, we got that 45 degree. After import that Kp, Ki, Kd values. We just look at the phase margin equal to 45. Then radian per second equal to 4. This is our design value. That is given value. Yeah, omega equal to 4. Then angle desired phase margin equal to 45 degree. Here I import in terms of radian. Okay. This is PID, then PD. Here that desired phase margin equal to 0.52 in I'm giving. So that actual degree 30 degree. So this program PD controller, that desired phase margin equal to 30 degree, then omega 1 equal to 1.2. So now I'm execute this program. .30 degree, then 1.2. So 30 degree is our given phase margin. Then omega 1, 1.2 is our given spec. So in frequency domain, the desired value of phase margin and gain crossover frequency. So we find out that Kp, Ki, and Kd values. That is other domain. No, earlier root locus technique we decided and discussed. So what are parameters given from time domain? So suppose the parameters given in frequency domain, so we can use this technique for the desired value of phase margin and gain crossover frequency. So the final conclusion, that the PID controller parameters tuning, it may be in time domain or frequency domain. So we can be able to design the Kp, Ki, Kd value with certain procedures. Okay, so that is of that main objective of this session. I hope everybody understanding what I'm telling. If any doubt, I can ask.
Participants, do you have any questions? Please raise your questions. If you have any queries, you can ask, or you can comment that questions in the text box also.
Not only this session, if you have any doubt related with tuning, can ask me. Not this time. Suppose you are doing any research work, you can contact me. No problem.
Sure, sir.
So
Some participants asking the PPT to share, sir.
I will share to your mail, sir.
Sure,
With
sure, sir.
PPT, same PPT, I'll send it to your mail or
Okay, sir.
Umayal madam mail ID I have. Better I can send it to madam. So better you can collect from madam.
Sure, sir. Sure, sir. I will.
Okay.
And I will release that mail.
Okay,
to
sir. You
all.
can share this PPT to everyone, no problem.
Okay.
Actually, this is the existing one. So they can use, no problem.
Okay, sir. Okay, sir. So,
So-
sir, reminder, sir.
So once again, I would like to thank to all participants and PSN College of Engineering Management and HOD of EEE department, and special thanks to Mayal madam. Actually, madam giving very good opportunity, share my knowledge. Actually, frankly, I'm telling this is my first guest lecture. I'm taking this guest lecture to other participants. So anyway, I'm very happy because I'm sharing my knowledge to everyone. So I'm very happy. So thank you for listening my class, lecture class. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you. Can I leave, sir?
Yes, sir. Yes, sir.
Thank you, sir. Okay, bye.
Thank you very much. Thank you.
Yeah.
Thank you, madam. Thank you.